Thank you. And thanks, Anna, for that really nice presentation. I think that'll set the kind of scene for this talk really well. So Anna, and specifically in the framework of the Oz eco models, has really done a good job in trying to start a lot of the stuff that Landfire has done in creating a kind of a nationwide or continental scale, I guess, suite of models to represent ecosystem dynamics in Australia, but at a very high level. You saw that very complicated map of Australian vegetation. That's a massive oversimplification of what's actually on the ground in Australia. And so I guess my kind of role is to think about how we can take those archetype models for a broad continental scale vegetation type and actually turn it into a product that at a landscape scale can actually make explicit predictions that are useful to people on the ground. So yeah, I'd like to start, as Anna said, it's a practice we have in Australia to acknowledge the traditional owners of the land on which we live and work and which our research takes place and where we're meeting. And I think it offers a really good opportunity to reflect on how we're connecting with kind of traditional knowledge and kind of a really deep ecological understanding. I think it's really important in the area we're working in to really reflect on that, because we're talking about in this room maybe hundreds of years at best of ecological knowledge, whereas people who've lived on this landscape for millennia, in the case in Australia, tens of thousands of years. There's a whole lot of knowledge there that we ignore at our own peril. So I think, and even further in this kind of state and transitioning modeling sphere that really relies a lot on expert elicitation, I think it's really important that we reflect on how we're engaging with traditional knowledge in that regard. So on that note, I'd like to acknowledge the Larrakia and Palawa people, the lands in which I live and work, the traditional owners of the lands of which I live and work, and where this research is taking place. And also on that note, the Arapaho, Cheyenne, and Ute nations, who have deep ancestral ties to landscapes on which we're meeting today. Also, I'd like to acknowledge the co-authors of this work, very involved with people across Australia and from the Nature Conservancy and ApexRMS. So we're really trying to think about how we can actually represent Australian ecosystems and state and transition models. And Anna and I are very lucky to have Louis Provencher to come over and work with us a little in November. And Louis and I kind of sat down, started to try to throw together some basic state and transition simulation models. And we realized there's one fundamentally different thing about Australian vegetation than really vegetation anywhere else, and that's the eucalypt. So eucalyptus trees dominate the majority of Australian vegetation types. And they have a wide range of forms. No. Well, anyway, so the one on the left there, that's the tallest flowering tree on the planet. It's over 100 meters tall. You go from that to 3-meter snow gums that exist in alpine areas, and everything in between. You get an incredible variety of form and function of eucalypts in Australia. And the thing about eucalypts, I'm sorry, to give you an idea of what their range looks like, these are all the vegetation types in Australia that are dominated by eucalyptus trees or shrubs. And if you overlay the map of the Australian population, you realize that if we're thinking about, especially if we're thinking about bushfire risk and risk of the wildland urban interface, we're really thinking about eucalyptus vegetation. So the thing about eucalypts is they really like to burn. They're very, very co-adapted with fire. While their seeds are not technically serotinous, they effectively are. They need gaps in the canopy and often fire to regenerate new pulses. Most species of eucalypt have the capacity to resprout both epicormically and basally following a fire. And if you look at a burnt landscape after a fire in eucalyptus forests or woodlands, you see this incredible response they have to surviving fire, and you'll get often epicormic resprouting. all up and down the stems. And with the exception of a few species and obligate seeding vegetation types, it's pretty much impossible to kill a eucalypt with fire unless it's very repeated in short intervals. So the upshot of all this is that transitions in eucalypt-dominated vegetation don't occur because of one fire, rather they occur because of shifting fire intervals. That's a very fundamental difference and something we really need to think about how we represent that in state and transition simulation models. So I'll give you two examples of this, which happen to be the two examples of my first two case studies in landscapes. In that we have wet eucalypt forests on the top, which are basically among the eucalypt forests have the longest interfire intervals on the continent, and then ranging from 70 to 300 years between fires. And you might have, if you remember the terminology Anna was talking about the variations within a reference state versus changing to a modified state. In these forests, you might have a single fire essentially resetting a successional pathway from mature forest to young forest. But if you get two fires within a short succession, you actually and kill off all the saplings before they develop, they start producing seed, you'll get a transition into a shrubland that's dominated by non-eucalypts, and you'll lose all your eucalypts. Similarly, in vegetation that may have the shortest interfire intervals, among the shortest interfire intervals in the world, in the tropical eucalypt savanna, some of which gets burnt every year, you'll have transitions between you'll have shifts between two expressions within the reference state based on fire frequency, shifting between grassy understories and understories with rainforesty shrubs and native conifers. But then if you get extremely high fire frequencies, and if you see on the bottom right there, combined with feral herbivores, you'll start to see actual shifts you'll start to lose most of your woody vegetation. And so I just want to give you a little animation here to show you how gradual some of these changes are. So this is an example of two tropical savannas, permanent plots we have in tropical savannas that had been long unburnt in their around 2010, and then have been monitored for roughly, I guess it would have been 2005, earlier, yeah. Been monitored for roughly 20 years, and these are two examples of plots that were burnt annually or biannually, and just to show you how kind of gradual some of this change is. So this is an annual burn every year, and you can see there's a very slow shift from a shrubby understory to a grassy understory, but it's not super detectable. This is similarly burnt every 2 years. It's not super detectable if you're looking at it, looking at the progression year by year. But if you look at the difference, so on the picture on the left is kind of the before 20 years of burning, and the picture on the right is after. You can see there's a really big difference in that you're selecting for lots of grasses, and particularly annual grasses. And I just wanted to kind of show how that's the kind of shifts we're looking at within state and transition models. It's not a single event that's causing that shift. It's rather changes in the fire interval. And this is a really dynamic we're really going to have to think about when we think about using state and transition models in this concept. So that being said, I just gave you these examples of complicated dynamics of how ecosystems actually work. The way they're represented in fire behavior models and fire risk models in Australia is quite simple. It's basically a function of it's a prediction. A fuel load is a function of time since fire. And this is a slide I like to show for my PhD. It shows what some of the forests I worked in actually looked like at different points along that time since fire progression. And you can see that the simple kind of asymptotic prediction of fuel load is missing a lot of the dynamics of microclimate and fuel arrangement that we know are very important for fire behavior. And so basically just to show you where historically we've been at with fire behavior prediction in Australia. Basically this is the MacArthur model, which is our version of the Rotherham model, which is the base of all fire behavior predictions in Australia historically. So you can see this is a massive oversimplification of what are very complex ecological dynamics. So this kind of sets the stage for what's been a really big movement over the last decade in Australia, which is essentially creating a whole new system of bushfire risk modeling. And I'll give you 3 kind of examples of this that'll be very relevant to this work. And essentially, the project I'm kind of attached to within CSIRO is called National Bushfire Intelligence Capability, and it's responsible for creating a nationally consistent set of fuels data that's been developed through consistent methodology, which currently doesn't exist in Australia. A new fire behavior simulator with new fire behavior models underpinning it. And all of that's going to is plugged into recently released new fire danger rating system. There's lots of levels of complexity to this. Time to get into them today, but happy to talk your ear off on them if you're interested. And then this kind of introduces within that kind of framework is this project I'm trying to develop. Was essentially, we're calling it AusEco Forecast to complement AusEco models, and it's essentially a process and tool, a process to create tools that at a landscape level can make spatially explicit predictions on how landscape management affects changes in vegetation into the future. It's basically what many of you in this room have been doing that we're really interested to implement in the Australian context. So the idea behind it is that we use expert elicitation. We take those archetype models that Anna talked about, and we use expert elicitation to basically edit them for a specific landscape. We then continue with the expert elicitation to actually develop quantitative metrics, specifically attributes associated with different states and expressions and probabilities of transition. And we combine that expert elicitation with a bunch of tools we have to understand how fire risk and landscape change are going to be affected by climate change, especially things like fire behavior models, plant growth models, and climate change projections. We use these to make forecasting, to make maps that specifically forecast how landscapes are going to change into the future. And these in turn can both plug into national products, such as the national scale fuel and fire risk models that I was talking about, along with helping land managers to make decisions at the local scale. So I'm going to do this with 2 case studies in Australia from the 2 kind of extremes of Australian vegetation. One, as I said, in Tasmanian tall wet eucalypt forests, which have the longest fire intervals of any eucalyptus vegetation in Australia, and have many other superlatives. And wet, dry savanna eucalypt woodland in the top end of Australia. So I'm not going to get into this second case study too much in this talk because we're really at the early stage of this research. But the savanna woodland in northern Australia, especially in Arnhem Land, which is the region we're going to be looking at, is possibly among the most continuously occupied by human, most continuously occupied by human areas on the planet outside of Africa. Humans have been there for over 60,000 years, and it has, compared to other parts of Australia, has been relatively unaffected by colonization. So there's a lot of deep ecological knowledge there. We're still at the point of the process of just developing relationships. So I don't have any results to show you at this point, but hopefully in 3 years at the next conference, I can show you some more outcomes. So I'm going to focus today on the case study in which I did my PhD and which I'm very, very closely connected with, the Tasmanian tall wet eucalypt forests, and specifically a region in southern Tasmania, which I know very well. So Tasmania, as I mentioned, Tasmanian tall wet eucalypt forests contain the tallest flowering trees on the planet. Actually, I always say that. That's actually not true. As of a couple of years ago, they found a taller one in Indonesia, but that's another story. But we'll just, it has better ring to it. But yeah, so they're defined by, they're really interesting, especially from a fire behavior perspective, because they're defined by having a eucalyptus overstory of extremely tall trees, and being eucalypts, they're highly flammable. But then they have very dense fire-sensitive mid-stories, essentially. So lots of rainforest, Gondwanan rainforest species and other species, they're very sensitive to fire in the mid-story, which kind of act as a buffer for fire, and they're actually very hard to ignite, hence the long inner fire intervals. And also very moist understory microclimates. So it's this very kind of ecosystem full of contrasts, and it makes them really interesting, also really hard to understand the role of fire. And part of my PhD was looking at a lot of the assumptions made about the role of fire in these ecosystems, and a lot of them were quite wrong, actually, just because there's just a very, until recently, poorly studied ecosystem. So we started this project within tall, wet eucalypt forests, using expert elicitation to kind of modify the AusEco model templates, and these are the 3 AusEco model templates. So I should say that our study landscape contains more than just tall, wet eucalypt forests. The tall, wet eucalypt forests are the dominant vegetation there. Interspersed among them, though, are many very globally significant vegetation types involving Gondwanan, many Gondwanan relics. So it's really there's a lot of dynamics at play here. So these were the 3 archetype models we used to start the process. We went through an expert elicitation, and we developed this simplified model, essentially. So for each of the states, so each of these green boxes represents a more complex submodel. And I won't go into each of the details of each one, but I'll just give you an example of what some of them look like. So this is the reference model for single cohort wet eucalypt forest. And you could just see that there's a fair amount of complexity in these. I'm kind of running out of time, but I just wanted to give an idea of this is what happens when you get a lot of experts into a room, and you had this overarching model and it turns into something a lot more complicated. But it was a really useful experience, and people were so enthusiastic about it. It was actually really exciting. We'd spent a day in the field, and it was really good to get all this this kind of framework for this conceptual model. So that's basically where we're at now. We have this conceptual model with, as I said, lots of complexity. I forgot how many there were in here. And essentially, we've gotten to the point where we've done that and used those models to create a map of what the current state is right now. So this map includes no remote sensing. It's, well, other than fire history, it includes no remote sensing. This is just based on the vegetation map and the fire history of what we think this landscape looks like at the moment. You can see the complexity in here. There's a lot going on. So I think at this point, we have to kind of, I guess, think about how we take all this complexity and get a working model out of it. And then, yeah, obviously the next steps are going to be start to think about how to attach quantitative values to those conceptual models. So I'm going to go over some ideas. One of the reasons for me coming here is to hear about all y'all's experience in actually doing this and actually getting spatially explicit predictions. But I think my ideas in terms of the next step, especially in terms of starting by identifying states and expressions on the landscape, or to use the remote sensing products we have available to us. We also have a lot of LiDAR data from this landscape, which is really exciting, from both before and after a recent wildfire in 2019. Maybe starting to think about getting into some predictive vegetation modeling as well, because some of this vegetation is really hard to identify with remote sensing due to its high productivity and validation with field data. So yeah, I just wanted to present, we're still pretty early in this process. We basically got to the conceptual model, the point of conceptual modeling, and really interested to hear everybody's experiences here, and if anybody has any perspectives they want to share. Yeah, just wanted to thank everybody, and yeah, thanks for your time.